Have you ever wondered how people find the speed of light? Light moves really fast, so it's hard.
Well, we found a way to measure the speed of light in the comfort of your own home. For your information, in this video, we'll be following the scientific method, and it all starts with a question. Here's ours.
What is the speed of electromagnetic waves in the microwave portion of the light spectrum? Can we find the speed of electromagnetic waves using a microwave oven?
Before we get into the actual experiment, here are some handy terms and information that you'll want to know.
Visible light moves in wavelengths within the electromagnetic spectrum. Each side of the spectrum can produce temperature, with the side to the left being infrared and producing heat, and the side to the right being ultraviolet light. Microwave wavelengths are another form of electromagnetic light. Microwave ovens utilize microwave wavelengths to cook food.
Because all light moves at the same speed, in measuring the speed of microwaves, you can find the speed of light.
Here are some key terms to know going into this experiment.
A wave's frequency is the number of waves that pass a certain point in a period of time.
A wavelength is the distance between successive crests or troughs.
A standing wave is the combination of two waves moving in opposite directions with the same amplitude and frequency.
When a wave crest interferes or collides with another crest, they combine to make a larger crest. When a wave trough interferes with another trough, they combine to make a larger trough.
When a wave trough and crest interfere, they cancel each other out. And this is the most important one. Frequency times wavelength equals wave speed.
Now let's get into this experiment.
First, we gathered our necessary materials.
Five naturally harvested organic eggs, a district office provision, various cups and bowls, a microwave, paper plates, and a ruler.
This experiment will be using the microwave oven and the interference inside it. The microwave wavelengths interfere with the object in the microwave at different spots. Interference patterns create different spots inside the microwave, hot and cold spots, where the energy is higher or lower than average. Distance between these hot spots happens to be equal to half the wavelength of microwaves, which can later be used to find the microwave speed.
Microwaves have rotating platters to stop uneven cooking and potentially hot or cold spots. We removed our rotating platter to use those hot and cold spots to find the frequency.
Hey everybody! So we cracked our eggs because we're gonna put the eggs in the microwave. So we put it into the bowl, which it would be microwave. That is a plate. We put it over this thingy so it wouldn't rotate. Then we turned on the microwave. Yeah, we turned it on. And then it started microwaving. And then Esther's nose started bleeding, really, but that's not important. No. But our egg exploded. This was our failure. We had to clean the microwave. It smelled so bad. This is what it looked like. Yeah, it was really bad. It was like not even like measurable. We were looking for the hot spots in the egg. Okay, this is our new attempt. This is attempt number 1. No, yeah, number 1. Yeah. We count it as number 1 because the other one was a fail. Yes. Yeah, because then it wouldn't get as hot. Yes, do you see these hot spots? That's the spots where the waves hit it. That's okay. You can see now we're measuring. We have to find the distance between the cooked spots, which are our hot spots. This is where the waves hit the egg in the microwave because it uses microwave waves. This one, it was a good measurement. It was pretty good. Okay, now we're cooking egg number 2. We had to repeat it a ton of times because it would give us the average. Ew, why are you drinking that? I know I'm not. Okay, now we're typing in a number. We ended up putting it in the microwave for 15 seconds.
Here's our gathered data. This is the measurements we got from our first egg. Here's our measurements from our second egg, our third egg, and our fourth egg, which was a little bit smaller. Now that we had the measurements between the hot spots of our eggs, we knew the wavelength part of our equation. With the frequency provided on the back of the microwave, we could plug everything into the wavelength times frequency formula and find the wave speed. Sadly, when we plugged all of our values into our equation, our answer was extremely small. Although our hypothesis was that our speed would be different, this was suspicious. In our exploration of the interwebs, we found a smart British lady who was performing a similar experiment, but with chocolate instead of eggs.
There was a key difference between our variables and hers, the frequency provided on the back of the microwave. But not any issues with our measurements or our calculations. Instead, it turned out that we had to convert the megahertz to hertz to give us an accurate wave speed.
Cute, that's really adding good things to this video. Our microwave speed was a value between 315,000 and 407,000. The number that scientists usually round to for the speed of light is 300,000. So, our hypothesis was wrong. Our found microwave speed was too close to the speed of light to be different.
All this to consider, we were essentially able to calculate the speed of light, roughly, but still very close to the actual speed of light. It's important to note that our measurements, although accurate, were very few, and for a more accurate number, we would want to take at least 30 sets of data.
Big shout out to Science Buddies! They have a step-by-step instruction tutorial that walked us through how to perform this experiment. Also, enormous shout out to the lady in Open College's chocolate video. She told us what we did wrong. And finally, thank you to all the district office employees that let us explode eggs in their microwaves. Oops!
Contract or no, I will not bow to any sponsor.
Maybe I'm wrong on this one, but for me, the beast doesn't include selling out.
I gotta go. I'm late for class.